let me remind you what we did last time. I explained that there's the moduli space construction. So you fix an Azumaya algebra and you fix the Hilbert polynomial, then we can talk about the moduli space of A chi. So this is, if you want, it's a moduli space in the Euclidean category of modules over the Azumaya algebra. And then there was the subtlety that if you have an equivalent Azumaya algebra, so what we really would like to have is a moduli space for each Brauer class. So we will need to compare the two moduli spaces for two equivalent Azumaya algebras. And then I have a moduli space here. In general, there's of course no reason why the Hilbert polynomial should be preserved, but there will be another Hilbert polynomial. But then this is in general not introducing isomorphism because these moduli spaces use Giesecke semi-stability. So we only have an isomorphism between the mu stable parts on the two sides. And moreover, if the two Azumaya algebras are not only equivalent but actually give the same class in the special Brauer group, that means the equivalence now is only between A and A tensor the homomorphism of a bundle with first Chern class. And we also assume, and I'm afraid I forgot this assumption last time, the rank of the two are the same. Then, in fact, the chi equals the chi prime. Because if you change A by tensor product with n morphisms of a bundle of n-morphisms of a vector bundle, or of the same bundle tensor by a line bundle of degree 0, the Hilbert polynomial will not change.
Can you say again who chi prime is? You have chi coming.
Yeah, so I mean, you just take here, so if the A prime, the standard example is, this is tensor NE, and then the equivalence would be given by F tensor E, and then the chi prime is such that it's chi of F tensor E of an F that has this kind. Okay? But, I mean, otherwise it doesn't make sense. I mean, of course, estimate. Otherwise, if you don't have this, then you might have to change something. Okay, so now I want to switch to K3 surfaces. So I take a K3 surface. I take an Azumaya algebra on S, and then I can. So usually, instead of looking at the Hilbert polynomial, we fix a Mucha vector. Mucha vector. So this would be the moduli space of semi-stable A modules with Mucha vector the given vector. What we can say is we can. Let me first give you this one theorem by Yoshioka. So that's old already. So if V is primitive and the polarization generic, then this moduli space is a hyperkähler. It's a hyperkähler of K3 and prime. And the primitive here means primitive as, so this vector cannot be written as a multiple of a Mucha vector of some other A module. So by the general theory, we know we can define moduli space of mu stable A modules that's then independent of the Azumaya algebra. So this is the module space of semi-stable A modules where A, the class of the Azumaya algebra, is fixed, but as an element in the special Brauer group of S. And now the Mucha vector here is actually the standard Mucha vector divided by the Chern of A. And the computation that this then is independent under the equivalence, so that's well defined. It doesn't depend on the choice of the Azumaya algebra anymore, as long as you fix the class in the special Brauer. Okay, so this comes out of the general theory, and then, but in fact, we find, and that's an accident, I think, that even this one is well defined. So again, alpha is fixed as a special class in the special Brauer group S. So we can talk about these models. And now I want to report on joint work with Dominique Mattei that hopefully will appear in the archive very soon. So we stick to a KP surface S, and we consider a linear system, a complete linear system. So that's a complete linear system on S. And we assume the generic curve is smooth, so generically smooth. And now I'm looking at the Mucha vector V alpha that looks so that realized by sheaves concentrated on the fibers on the curves in this linear system. So the Mucha vector then would look like H, and then there's a value here, and this one is I forgot what it is. It is some S, and note that this, let me look at this. Okay, so then we have this moduli space. So M alpha V alpha parameterizes A modules concentrated on curves C in the linear system with a certain Mucha vector. I think yes. Okay. I think we pick S to be 1 minus G, where G of course is the means of the curve. Then the degree of those sheaves is 0. So now the moduli space we want to consider is this moduli space. So we consider M alpha, and then the Mucha vector is 0 H sub S. The usual support map fibers has this moduli space over the linear system H. So now let's look at the generic curve. So let's look at a smooth curve. At a smooth curve C in the linear system, and look at the fiber over this curve. Okay, what's the fiber? So well, the fiber consists of all coherent sheaves concentrated on this fiber, and which have an A module structure. But an A module structure means it's has the structure of an A restricted to C module. Okay, and now and the rank of E, because here essentially I divide by the rank by the square root of the rank of the Azumaya algebra. This thing is the same as the rank of A, and then square root, and then plus some degree, which is of no importance for us. So this is how the fiber looks like. So now, if C is a smooth curve, the Brauer group of a smooth curve is just 0. So Brauer group of C is just trivial, and that means this Azumaya algebra is equivalent to the trivial to OX. So I can write AC as endomorphism of E. Okay, so it doesn't need to be any of those E's, but if the fiber is non-empty, so these moduli spaces might be empty, depending on the parameters you chose, but if this fiber is not empty, we can actually choose one of those E parameterized here. So if the moduli space is not empty, then just choose this E in one of those fibers.
Sorry, let's slow down. Like this V alpha. So previously the alpha was V divided by something, right? So what's the meaning of the alpha now in this?
It's still this V, the usual Mucha vector divided by, and now this, because we only have things in degree 1 and 2, I just divide by the square root of the rank, so by the degree of the Azumaya algebra.
So you fix a V, which you don't write, and then the alpha is that V divided.
Right. Right. So the V alpha is well defined. The V is not well defined because that depends on the Azumaya algebra. Right? So this does not depend on the choice of A, but the Mucha vector will depend. That changes by the Chern character of A. So this V alpha is well defined, doesn't depend on the choice of the Azumaya algebra, representing this class alpha in the special law.
Can I ask, why don't you use the Gm-gerbes so you have a Chern character?
Well, I mentioned gerbes at the beginning, but I never explained really the link. You can. I mean, there's an equivalent theory, which is.
Then you have a Chern character.
So first of all, yeah, I have to work with a mu n-gerbe. I cannot work with a Gm-gerbe.
So mu and the Chern character depends from the choice of an invertible.
No. This because the mu n-gerbe, I mentioned it very early, but maybe you weren't here. The mu n-gerbe, this is a linear Mumford stack. So there's a natural stability condition. This is what Lieblich does. That's an equivalent point of view. Okay.
Daniel, the degree of E between gamma E.
The degree, yes, yeah. So this S here is the degree of E divided again by the square root of Azumaya. So now, if there is something in the fiber, so I can pick one E, then the Azumaya algebra AC is just isomorphic to the endomorphism bundle, and then every other point in the fiber is actually obtained just as E twisted by some line bundle on C. So in other words, the fiber here is a torsor over peak 0. F minus 1 of E of C is a torsor for peak 0 of C. Okay.
Can you explain again why there's this L, so why E prime and D differ by L?
So if you have two bundles giving the same Azumaya algebra, so that means the endomorphisms are the same, and then they differ by a line bundle. That holds for twisted bundles as well as for untwisted. Well, here they are just bundles. Sorry. Okay. So now what do we have? We have this our moduli space M alpha D alpha that sits over the linear system H. If I restrict to the smooth part of the linear system, then I get something that are torsors under peak 0, and it makes sense somehow to denote those fibers as peak alpha. Then there's a certain D, And I think the link between D and S is something like this, plus or minus, always forget. And then I have the pig D twisted relative over the smooth part. And this thing here is a torso for the pig 0 of the smooth curve over the linear system. Okay. So the moduli space is the compactification. So in this sense, we could write this as compactification of something that depends on the Brauer class. There is an ambiguity, so I never told you. I mean, there is of course a dependence on the polarization. Stability depends on the class. This part, just by the very description, doesn't depend on the polarization. This part might. So this compactification business might depend on the polarization. Okay. And then there's this so which where we use the result by Markman, and then we interpret this by saying if X is a hyperkähler of K3n type with a Lagrangian fibration over Pn, then there exists the K3 surface S plus a Brauer class, so class in the special Brauer group of S, such that X is birational to the pig 0 D and the linear system, of course, NC over H, such that the X, your writing is this thing pig X birational to this one.
You text to be general.
There's one assumption which is probably in the end superfluous, but assume X is non-special. So that means there's no rational class in this part. Okay, so every Lagrangian fibration of a hyperkähler of K3n type, unless it's special, but probably we don't need this assumption, is one of those torsos given as the twisted Picard variety. You can even fix the degrees to be 0, and alpha is a class in the special. Okay, so this finishes Tuesday.
Sorry, you're assuming the X is not special or S?
X, I'm sorry.
Yeah.
Thank you. In the end, it's the same, but, but it makes more sense to put it as an assumption on X. Thank you.
If I'm allowed to the form X, do I still need the Brauer class?
Well, that depends how much you're willing to do. Thank you.
Inside the divisor within the Lagrangian fibration.
No, I think then you get away with untwisted. Well, well, it depends. So Markman proves something where he uses moduli space of untwisted sheaves. We just reinterpret his. And no, he says it's a Tate-Shafarevich twist of something untwisted, and we interpret this Tate-Shafarevich twist as a relative Picard, twisted relative Picard. I'm not sure you get away without any twists. I'm not sure. So I now start a new topic, which seems unrelated to except that I still talk about Brauer groups. But there is in fact a connection, which I hope to explain. And this is about, so this will be part 3, about splitting Brauer classes. Let me first explain what it means to split a Brauer class, and then I present to record some classical theory. So what's the problem? The problem is, suppose that we have a variety X, we have a Brauer class on X, and then we say that the morphism f from Y to X splits alpha if under the induced pullback, so there's always by concatenality a morphism from Brauer of X to Brauer Y, alpha is mapped to 1. So this morphism splits the Brauer class, so makes it trivial. So for instance, you could take Y point. If you work over an algebraically closed field, you pick a closed point in X, and then of course if you pull back alpha, since the Brauer group of a closed point will be trivial, it's trivial for an algebraically closed field, that will always split the alpha. Okay, so there's one example, there's one mother of all splittings. This is the Brauer Severi variety itself. So assume some alpha is represented by some Brauer Severi. Then the claim is this projection from the Brauer Severi actually splits alpha. So P splits the Brauer class. We discussed this before already, but I didn't give the argument. Now I will give the argument. Splits alpha. So for this, you observe the following. If you take, so what is the pullback of alpha? If alpha is represented by this Brauer Severi variety, the pullback of alpha will be represented by the pullback of the Brauer Severi variety. What's the pullback of the Brauer Severi variety on itself? Well, this is just the fiber product of P with itself over X. And then one finds out that this thing here is nothing but the projectivization of this extended tangent bundle. Let me recall there was this unique, so this was the version of the Euler sequence for Brauer Severi varieties. Just a quick check. So if this is if P was a Pn-1 bundle, that's a vector bundle of rank n-1. This is a vector bundle of rank n. So its projectivization really is again a Pn-1 bundle, and it turns out this is isomorphic to this one. And just writing this Brauer Severi variety as the projectivization of a projective bundle of a vector bundle tells you it's a trivial class. Okay. So in general, if a morphism from Y to X splits, if F splits alpha, and we represent alpha by some Brauer Severi variety, that means that the pullback once again is represented by the Brauer Severi variety obtained as the fiber product pullback of P. And the Brauer Severi variety of a variety gives a trivial Brauer class if and only if it has a rational section. Okay? Then Py has a rational section. This is the rational section. But this means if I have a rational section here, then of course I have a rational lift here. Hence, f alpha star, f star of alpha is trivial, so while f splits, if and only if the pullback, if and only if there exists a rational lift of f. So that means I have my morphism from Y to X, I have my Brauer Severi variety, and there's a rational lift of f.
Does it use smoothness of Y as before?
No, this smoothness was only when I wanted to close this thing over an open set. Yeah. True. Yes, let me know. Okay. So, what does it mean in order to understand how to split Brauer classes? We are looking for, you could now start with anything that maps to P and define your F as the composition. So anything that's obtained, any F obtained as a composition will split the alpha. Okay. So in other words, we're looking for instance, for subschemes of P. Every subscheme of P will split X. So this is the problem, but of course the splitting problem of Brauer classes, this is something very algebraic. So that has been studied for more than 100 years. In the case of simple algebras over fields. So I thought at this point maybe I can make a little interlude and recall some basic facts from algebra, and then I will reinterpret these facts geometrically. So in order to give you a feeling how the algebraic theory fits together with the more geometric we're looking at here. Okay. So just really some basic things. So classical theory. So we start with a field K, and we look at central simple K algebras, always finite dimensional. So the only ideals left and right ideals are two-sided ideals are 0 in the whole, and the center of this is K. K is in the center of the. Okay, so what's the first result we learn about these things? This is Wedderburn's theorem that says if A is a central simple algebra over K, then A is in fact matrix algebra over some division algebra, so D is a division algebra. And moreover, D is unique. So this is Wedderburn's theorem, and then one defines two algebras A1 to be equivalent. So I can write this one as Mn1 of D1. I can write this as Mn2 of some other division algebra, and you find this to be equivalent if and only if the division algebras are the same. And with this definition, you can then introduce the Brauer group of K, which is the set of all simple algebras divided by this equivalence relation. You might wonder, why do I talk about, when people talk about central simple algebras and not just about division algebras? The point is, if you want to make the Brauer group into a group, you need to define the product, and the product is given by the tensor product of algebras. But the tensor product of two division algebras is not necessarily division algebra, but only a central simple algebra. So in order to explain the product here, you have to talk about central simple algebras. Also note that if you have two central simple algebras, A1, A2 of the same dimension, then in fact A1 is equivalent to A2 if and only if A1 is isomorphic to A2. And I'll come back to this in the geometric. So that's the first result. The second one is if I have a central simple algebra, then there exists a finite separable extension that actually splits the algebra. So if I take the base change from A of course, somehow the pullback of A to L gives you simple algebra, and you want this to be to split. So that means A tensor L is equivalent to L. Okay, and you might want to define the splitting degree as splitting degree of A to be the minimum of all those degrees, or the DCAD of all those split A. Right, so this means we rephrase this by saying the class of A is in the kernel of the pullback map from the Brauer group of K to the Brauer group of L. The kernel is usually called the relative Brauer group of this Huybrechts. Note in particular that this way we prove that the Brauer group we define here is in fact nothing but the Brauer group, the Brauer Brauer group where I take spec K, because after finite separable extension, so after the eta cover, everything becomes trivial, so we can identify this to the Galois moduli coefficients in Gm. Okay.
What about saying splitting technique definition logs were?
So this take the minimal degree of all L's that split A. So for which alpha is in the A is in the kernel. Okay. The third fact is, so which I find a little confusing, the period of an Azumaya algebra is actually just the order of its class in the Brauer group. So this is the Brauer group. Okay. And if I fix the class alpha, if I denote this class by, if I call this class alpha, then the period is also called the period of alpha. By definition, that doesn't depend on the Azumaya, but only on the alpha. So when people talk about the period of the Brauer class, that means just the order. And then there's sometimes some people also call this exponent. So it's just the order. And then there's the index of alpha, and this is the minimum of. I can say it like this. This is the dimension of D and then square root for D, the division algebra representing alpha. So there's every class in the Brauer group is represented by a unique division algebra, and you take its dimension, and it's always a square, and then you take the square root. Or in other words, it's the minimal. That's also sometimes called the degree, the minimal degree of an Azumaya algebra representing the alpha. Okay. So that's the definition. And the fact then is that the period always, period of alpha always divides its index. You can be a bit more precise, namely a to the power of the index is, you prove that, this is how you prove it, is equivalent to the trivial algebra. And in particular, since the index by definition is of course a finite number, that tells you that the Brauer group is a torsion group. Okay. Now there's a link between the index and the splitting degree. So that's why somehow people don't talk about the splitting degree. It turns out the minimal degree that you need to split Brauer class is in fact just the index. Part 4. the index of alpha is the splitting degree of alpha. And finally, for which I don't have a geometric intuition, the prime factors of the index and the period are the same. Or in other words, the index always defines the period, some power of the period, but the n alpha might depend on alpha. Okay. And the period index problem is, so that's an old problem in a geometric situation, much studied by De Jong and students, is the question, can we bound, what is n? What is n? Alpha, for instance, is there one that works for all alphas? So is there maybe a power of the period that bounds the index? And the answer is yes for certain fields. So n alpha is 1 for number fields and some other nice fields. And De Jong in characteristic 0, and then Lieblich in positive characteristic, they show the n alpha is 1 if K is the function field of a surface, so where this is a surface of an algebraically closed field. Okay. And there is a conjecture that has been advocated by De Jong, that maybe if K is the function field of a variety of an algebraically closed field, then maybe the n alpha can always be chosen to be a dimension of x minus 1. So this assumption to work over an algebraically closed field, that has to be put in, because otherwise it's about the Brauer group of the base field is always around, and then if you don't put any assumption on the Brauer on the base field, then you can open anything. And of course, for an algebraically closed field, this is the Brauer group is trivial. So now I want to go through this list essentially again and explain what happens in the geometric setting. And some of these statements actually have quite, some things are different, and some things have a nice geometric interpretations. So the geometric perspective. Okay, so x, assume x is smooth quasi-projective, let's say, projected. Then it's known that for all big open subsets, so that means the codimension of its complement is at least 2. The Brauer group of x is the same as the Brauer group of u, and eventually this gives you an injection of the Brauer group of x into the Brauer group of kx. So the link between the geometric theory, so between Grothendieck's Brauer group of a scheme and the classical is via the function field. Okay, so that's the message. And so the method, of course, is just given by you take an Azumaya algebra and then you restrict it to a generic point. So that's an Azumaya algebra now over the one-pointed scheme, which is a spec of kx, and that's nothing but a simple algebra over the function field. Okay, so this is the method. Now I want to look at the first statement at Wedderburn's theorem. So now I have to maybe. Well, you have it in your notes, I hope. So there's this Wedderburn theorem. I need a little bit more space. And the question would be: is there something similar for the Brauer group? Oops. For the Brauer group of this.
May I have a question? For the second statement there,
So it implies that if K is algebraic closed, then the split equates 1.
Right.
Okay, and then how everything is 1.
Everything is 1, yeah. So for an algebraic closed field, there's no theory. So that's why if we work, for instance, over C over an algebraically closed field, there's nothing that happens in the closed points. Everything happens in the non-closed point. And the most interesting of those is, of course, the generic pointer. Okay, so for this, I'll go back to 1. So we have the, remind you of this, of our big diagram. So we have the commodity sequence here. And we go to H1 XPGL, and then we go to the Brauer group X, which is H2 Gm. You can, of course, write down the same thing for the function field. And you have the restriction maps, actually. Okay, it's again the function field here, and this is H2 of K. Gm. So first of all, H1 with relation to Gm is, of course, the Picard group. The Picard group of a point is just trivial. Okay, so this map is nothing. H1 with relation to Gn is also nothing because these are just vector bundles on a point, so these are just vector spaces. There's only one. But this group, of course, here, this already the Picard group can be big, but this can be enormous. So there's a huge kernel in here. Okay, and then of course, you do expect a huge kernel of this morphism of this map as well. So there are many, if you want, Brauer Severi variety on X that will restrict to the trivial Brauer Severi variety on the generic point. No, I shouldn't say it like this. Okay. And this map is injective. So here we have big phi with, for instance, if you take the trivial one, all the projectization of vector bundles will give you things here. But in a way, some of the fibers of the kernel, if you want, the fibers of this map here all come from here because this map is injective. Okay, so Wedderburn now tells us that this map is injective because there was this remark: if I have two Azumaya, so two central simple algebras of the same rank, giving the same class in the Brauer group, they're actually the same because then some of their matrix algebras over the same division ring, algebra, and so this one is injective. But we certainly don't have injectivity here. So Wedderburn's theorem does not hold for the Brauer group of schemes. Okay.
Daniel, you said you take the Brauer variety, you restrict it to the general point, and in general it will become trivial.
If for instance, if I projectivize a vector bundle, right, then of course if I restrict here, I get something trivial. But if you take something that does not come from here, that gives a non-trivial element here, then of course because of the injectivity cannot become trivial.
I think you need K prime.
There's no K prime.
Extension.
Again?
In the second line of your diagram. Oh, no, never mind. Because you had the K prime.
No, this prime was removed. Sorry. Okay, so the second thing now is yes. So The second statement was about the fact I recalled was about splitting a Brauer class by a finite extension. And so if alpha is represented by a Brauer Severi variety, then of course I can just take hyperplane sections in P over X to produce something that's generically finite over X. So pick Y in P such that this is generically finite. We call this F, and then F star alpha is of course nothing but the restriction of a Brauer class, first to the Brauer Severi variety, and then restricted to Y, but the pullback to the Brauer Severi is already trivial. So that means geometrically I find the generically finite morphism Y to X that splits the Brauer class alpha, and in particular, so I have Brauer X going to Y. Then here this is built into the function field, and I can even assume that Y is smooth, and I go to the function field of Y, and then at least this proves geometrically that every Brauer class for the function field that comes from X, so these are called unramified Brauer classes, splits under this finite extension, and of course AY is a finite extension. Well, if you want, this is a geometric way of proving this way. Then there was this statement about the period dividing the index. Here, of course, I first have to tell you what it means, the period in the index for alpha. So the period, of course, is just is again the order of the Brauer class of the class in the Brauer group of X. In the index now, this is the minimal rank, and then the square root of any Azumaya algebra realizing the class alpha. The definition was in a way easier in the algebraic situation because then I just took the dimension, square root of the dimension of the division algebra. But there is no unique thing. There is no analog of the division algebra for in the geometric situation. And what's the proof? Maybe I put this here. What's the argument here? Well, this is we come back to the definition of the Brauer group. This map here factorized via the boundary map to H to mu n. So the n, so the minimal n. So I have my class alpha here. The minimal n so that the alpha is an image of this morphism is the index. And if I have this index, if I have the class here that maps to alpha, then it actually maps. This map factorizes through this H2 of mu n. That means this class alpha is n torsion. Alpha n is 0, and that means the period of alpha really divides the index. So that's a purely homological argument. Okay. And there was something about the splitting degree being the index. Let me tell you how this is done.
But this point we also follows from the thing about the field, right? Because the index of
yes, you can do this by the field. This is slightly stronger in the sense that I realize the class on a scheme and not just on the function field. But this is just meant somehow to give you some geometric intuition why these things in the algebraic world hold actually true. And I find this quite satisfying that you do have a definition. Maybe the next one is actually the most interesting one. So this is about the splitting field, the splitting degree. By the way, there's one problem which I wasn't able to answer. So if I take the injection of the Brauer group into the Brauer of X into the Brauer group of the function field, then I have alpha here and I have the restriction. And of course, since this is an injection, the order of alpha, so the period of alpha, is the same as the period of alpha restricted to k. And we can show that the index of alpha is at least the index of alpha k. But I don't know whether I actually have equality there as well. Now my feeling is there's no reason for it. I haven't seen this. Okay, so now part 4. We start again with the Brauer Severi writing. Before I told you how to split it by a generically finite, any generically finite morphism here, but just by taking hyperplane section of P. That you can always do, but that doesn't allow you any control over the degree of this map. Now I'm doing something slightly slicker. I look at the section of the tangent bundle, and then I twist this high enough by some okay. And look at its 0 section. In X. So what do we expect? How many? What's the degree of this thing? First of all, fiber-wise, this is a rank n-1 bundle. So this is a Pn-1 bundle. This is fiber-wise a rank n-1 bundle. If you take a generic section of this one, so it looks like the tangent bundle of the projective space of dimension n-1. If you take a generic section, that's a section of rank n-1 bundle that will vanish in number of points. What's the number of points? The number of points is the second Chern class of this bundle, which is the top Chern class of this bundle, which for projective space of dimension n-1 happens to be n. Okay. This then is P X, and this is degree n-1. So the point is here that Cn-1 of Tpn-1 is n. And this tells you that the splitting degree is smaller than the index of alpha. You can actually prove equality. So the fact that the splitting index equals the index in the geometric world is the fact that the Chern number of a projective space is n+1. Okay. And so the geometric version now of the index.
What you're using, the ampleness of the tangent?
Yes, so this is relative ample, and then I twist it so I'm going to get a global section. Geometric version of the period index problem. Problem is if you have, let's say, smooth projective, take any Brauer class, and we know there exists an n such that the period of n, so its order, is divides the index of alpha to some power n alpha, and the question is, can we bound n alpha? So this is strictly weaker than the original question because we are only talking about the so-called unramified Brauer class, and those that on the function field that come from the scheme.
Because the index is eventually different, right? The index of the generic point and the global index are different.
That's what I you mean the index of the class? Yeah. So I expect this one to be bigger, but
it is a different question from index of the function.
That's true. If there's real difference here, and then also something that does depend on alpha, then there's also difference. Okay, now. Okay, maybe I'll give you two more examples. So this is about splitting Brauer classes via something finite field extension or generically finite morphisms. So this is classical theory, which is something that's less classical is splitting Brauer classes by morphisms with which are not generically finite. Of course, we do have this example that every Brauer class is split by its own Brauer Severi variety, but that's like the thing you always have. You want to have something geometrically more interesting. And there were a couple of things put forward. Oh, maybe I can mention those. Okay, so this would be a core of high dimensions. So the first example is we take a section of P. So again, alpha is represented by some Severi class, a Severi variety, and then we take a section of the relative canonical dual. So it's the relative canonical, and then this might not have any section globally. Then we twist it by a big power of some polarization coming from downstairs. So fiber-wise, this is the anti-canonical divisor, which of course in a projective space has plenty of sections. The funny thing is, if you now look at zero set, this thing here, so this the fibers here are projective space, and I take an anti-canonical hypersurface. That means the Calabi-Yau once it's smooth. So we split every Brauer class can be split by Calabi-Yau. Okay. Every Brauer class is split by Calabi-Yau. That's kind of amusing. The problem here is, of course, this Calabi-Yau, as the Brauer Severi variety, its dimension depends on the order of alpha.
You mean family of Calabi-Yau?
Yeah, so it's a family, it's a Calabi-Yau over the function field. But its dimension depends on alpha, or on the order of alpha. Of course, we can always split, a second example, we can always split by curves. So by taking C to be H1, Hn minus 2 inside of the P of X, this is a Pn-1 bundle, and these HIs are hyper, and let's say variable sections. And again, this means that every Brauer class can be split by curve over its function field. Okay, so that means we find something whose dimension does not depend on Brauer class. That's nice, but in general, the genus will depend. However, the genus of C will depend on the order of alpha, and the fact here is that the order of alpha divides 2g minus 2. So if you want curves of a fixed genus to split your Brauer class, you have to bound the order of the Brauer class. There's one exception, namely if g is 1. So g equals 1 has the potential to work for all classes alpha. Okay? And this is a question that's recent. I think it goes back to Clark and Saltman, but there's an earlier work, so that goes back to 66 by Roquette, and they ask if alpha is a class over some field, does there exist, so that's the question, does there exist a curve of genus 1 that splits alpha. So this is the question, and maybe I'll have to say something about this, but I'll do this tomorrow.